Hello everyone. So we're going to move into section number 2 in your unit 4. This lecture will be a short lecture and also our next one will be a short lecture too. So in this section, I am planning to discuss about optical devices, especially, you know, that the microscope and telescope. It's basically combination of the lenses. So we're going to discuss how to get the image formation by using at least two lens combinations. So we'll be converging, or maybe diverging, converging, but we're going to discuss how to analyze that kind of problem. So now you know that in microscope is the purpose of making larger image, right? So we're going to discuss how we can get the magnified image by using microscope and also how the magnification work in telescope. So in addition to that, we're going to go over a little bit about the accommodation that we need for our vision, because sometimes we can see nearsightedness, some people can see farsightedness, so we need to accommodate accordingly. So now, how do we use converging and diverging lens to accommodate our eye? So those are the plans for the chapter. So now this chapter in your textbook will be chapter number 26. Okay, so mainly it will be in chapter 26. Okay, so now let's move into the presentation. Okay, so first one is camera. So everybody know that the camera have a lens. It will be basically a converging lens. And we have, as example, if I put the object in front of the camera, then that object, the light coming from outside will hit the object and it will go to the lens that I have it in here, right? And then it will converge to the this image. You see that in here, image, and that will be a kind of like we can call it as light sensitive component. We have the behind the lens that will be a CCD, or it can be something that we can add like film or something, right? So now that is where the image going to create. So now especially there is a chamber in here, we call it as light tight chamber, and then definitely there is a converging lens, and that will create a real image to make a film or the CCD. So now what is actually happening in the camera, you know that you can focus the object or image better by changing the some length. What length should I change? So this length from object to lens will be your objective length or the distance, and then this lens to this CCD all the way to the right will be the image distance, right? So now we know that we can definitely change the object length by moving the camera back and forth, and in addition to that you can change the distance between the lens and the your this light sensitive component CCD or the film. So that will be able to focus as you need, right? That's the distance that you can change inside the camera, right? And then there is a shutter. So that is a mechanical device that will be open for selected time interval that basically we call it as the exposure time, right? So that's how usually camera work. But what we can include in the physics is basically this position of the lens and the distance to the object, and also distance to the image you can change, and then you can get the best image to the CCD tape. Okay. So now human eye. So human eye, everybody know that it's a very, very special eye that we have that all the eyes that we have is combined into our whole nerve system, because it's remarkable that we can see the images, we can see the very detailed information about the object and also colorful objects. So this is a remarkable thing that we all have, right? So, but this how this eye will work. So normal vision means basically, I would say normal vision is the vision that we usually can see, but some of the visions that we have to use the eyeglasses, or we have to use the magnifying glasses to make it perfect for some people that need accommodation for the eyes, right? But actually what is happening in here, simple example, if I keep the object in front of the eye, so then light rays hit the object, then it will go to your eye in this way, right? Number 1 and number 2 ray and 3 and 4 ray, and then it will converge from the converging lens that we have. And but there is a very special thing behind our eye, so that is basically the screen that we can project the image to, right? Now, where this accommodation coming from? This image that you have it in here, sometime will not focus into this place. So that may be focused into a different place. At that time, we need to do the eye accommodation to bring it to the correct screen, right? So this will be creating in here, but sometime it will create somewhere here, sometime it will create back, all the way back. That is not possible to get the image to the location we need. That nerve system can detect the signal from the what you are seeing from your eye, because it should go to your brain through the light nerve system, and then it will send you the signal that you identify this object, and like that. It's a very big process happening inside, but the physics is here. So you have converging lens. So your image should be focused into a disk that we have it on the back or the screen. And if it is not automatically focusing into there, then we need the accommodation in front of the eye. So it can be a converging lens, or it can be a diverging lens, depending on the accommodation we need. Okay. So, yeah, so we have basically two problems. One is nearsightedness. Some people have nearsightedness. That means they can see near object, but they have a problem with seeing far object. That is called it as nearsightedness. And farsightedness means you can see far away object, but it is difficult to focus into closer object. That is called it as farsightedness. So now actually what is happening in the eye cartoon, you see that here in nearsightedness, actually what is happening is your vision that you watching the object, far away object, but that object will not create the image exactly on this position. It will create the image little before that. Right? So now we know what I have to do. I need to bring this one to the screen. How do I bring it? To do that, you know that you need to spread out a little bit. So to do that, only way we can do is by using diverging lens. So diverging lens diverge the light. Because of that, that is the best option for that kind of accommodation. So now farsightedness will be little different from that, because in farsightedness, if you have a closer object, you're going to see that object behind your screen. Okay, so that means not focus. So at that time, I need to bring this point to the screen. So to do that, definitely I can use the converging lens, because converging lens converge the light little towards the axis, optical axis. Now this one we can accommodate by using converging lens. Okay, so I have the diagrams in the bottom. So if somebody have both sideness, then definitely we need to accommodate with the part of the glass with the converging, and part of that is diverging. So, and there are many modification of the lenses that we can do according to the problem we have on the our eyes. But this is main two effects that we can easily discuss by using converging and diverging lens. Okay. And so now thin lens system. So why I need to talk about the thin lens system? Because you know that microscope, telescope, or any optical devices, we have two lens or more lenses in the setup or device, right? But if you know how to work with the two lens, then you will be able to work with the three lens, because you just keep repeating the same thing, right? But two lens also, there is nothing new, since you know how to work with the one lens system. So when you include the two lens, basically you're going to create the image from first lens, and that image will be an object to the second lens, then it will create the last image. So that's the basically the process it will happen, right? So let's move into this diagram that I have here. So this diagram, it's my first one, right? So I have kangaroo. So we'll say I have some object and distance D1, so to the lens, and then it will create an image here. This is my first image created by object that I have it in here. And I have the first lens in here. That is lens number 1. Right after I realize that the location of the image from the first lens, I will not worry about the things happen before that. Now I'm going to insert or add my second lens to the problem and work from there. So now I am done with the first one. Now I am going to include the second lens. Now this will be my object. That object created by the first lens, right? This is the image created by the first lens, but it will be an object to the second lens. So now my second lens is here. This is the second lens, right? So now second lens will create an image somewhere here, right? So that will be your last image. This is the last image, right? So your object is kangaroo beginning. Now it will create the image I all the way to the right. That is the combination image, combination of lens image, right? So now it is easy to work. You use the exactly your lens equation for the first problem and find the image position, and then keep your second lens and take that image as an object to the second lens, and then use your lens equation to solve your final problem, and magnification and those things also easily solvable accordingly. Right? So now this will be the same for any case, but you know that converging lens depend on the place that you're going to keep. It will create the image in different places, right? So now simple example, I have it in here. If you create the image on here, but I keep the second lens somewhere here in the B, second lens I'm going to keep before your image, then it will create the image in somewhere here. Oops, somewhere my pen does something. So somewhere here, that will be the image location. If you keep the lens, in this case, to the left of the first image, then second image will be created like this. So now you can change the position of your second lens into different places. And here I have the lens very close to the image. We know that it will create a image that will be very big, that you can see somewhere here on the other side, right? And then converging lens work like that. And also I have diverging lens information in here. Using divergence together, sometime not be very useful, but converging and diverging together will be a useful way to create the image that we need for our purpose. Okay, so now let's move into the little bit about the optical instruments. And first one, I would say simple magnifying lens or simple microscope, right? So now we call it as the near point or near length that we can have usually will be 25 centimeters for I would say ideal eye. So we all don't have it, but that will be around 25 centimeters. If you keep your finger, you can watch. It is very clear. If you don't have any eye problem, then it will be focused exactly at 25 centimeters. That is, we call it as near point, right? But some people have the problem that is not able to focus at 25 centimeters. Then what we can do is we can bring a converging lens, but with the focal length should be less than the 25. Okay, so you're going to use the converging lens in front of the eye. The focal point should be less than 25, right? And you need to use the correct lens accordingly. I would say in like big wise, it is less than 25 centimeter lens. So you're going to put that in front of your eye, and then you will be able to project your image into the focus place. So this is, we call it as a simple microscope. Simple, the eye problem that we can solve actually by using converging lens, right? So now the magnification of this kind of simple microscope will be, this is not exact because we are doing some kind of conceptual understanding. We are not going to calculate it exactly, but it is approximately, okay? So it is approximately 25 divided by the focal length of the lens that you're going to use. Okay, that will be the magnification of the simple microscope. Okay. So now we can move into the compound microscope. So compound microscope have two lenses. One is the eyepiece that you have closer to your eye, and other one we call it as the objective lens that is closer to the object. So now any microscope purpose is creating larger in size image, right? So now in this case, actually the ray diagram, I have it in here. So now your objective is actually very small. Like if you are watching the cell structure, that through the microscope, that object is a very tiny object, right? So that's what we need to make it larger to get more detailed information. So now if you keep the object in front of your objective lens, converging lens I'm going to use, then your image will create somewhere here. This is the image from objective lens or from the lens number 1. So now that will be an object to your second lens, that is the eyepiece, and that will create, you see that the focal, it is creating the image closer to the focal point or to the side of the lens. Then it will create the magnifying image. If you go back to your earlier session, you will be able to see that ray diagram. This is exactly what is happening. Then you're going to send the rays from this one, and you are watching in this side. These two rays are going to intercept somewhere here. Then this will be your last image that you're going to see. Okay. So now magnification of this problem, again, we can calculate by using this formula. So you don't want to derive it, you can directly use that to calculate the magnification of the compound microscope. So now what those parameters, we have 25 centimeters, as we know, that is the near point of the ideal eye. And then I have eyepiece focal point. This is eyepiece focal point. This is objective lens focal point. S is there. S is the distance. You see that here. So your distance between two focal points, this distance. Okay. Distance between two focal points, we call it as the S. And also there is a negative sign because definitely it will create inverted image because of that is negative. Okay, so that's the formula to find the magnification if it is a compound microscope. Okay. Okay, so now let's move into the refracting telescope. So in this telescope, we have again eyepiece and the objective, but the telescope meaning is we're going to observe the faraway object like sky or some other stars that we're going to observe. Telescope will be useful for that case, right? So now in here also, as you can see, there is objective and eyepiece. So the earlier telescope, the first telescope that developed may had the actually divergent lens. Okay, so but this one we have the two convergent lens. One is objective and one is the eyepiece. So now when you send the light to the first objective, you see that far away image. You're going to watch the stars basically. So when you observe the stars by using the first one, definitely parallel rays will go to the focal point. That's why we have this, your object is created at the focal point, right? That is the focal point of the objective lens. So that will be the image created by the objective lens. Now eyepiece going to use to create a second image. Now this will be the object and this is where you're going to see. And then you're going to create the image. It's not drawn in this diagram. It's going to create the image in by combining these two lines. That will be the image that you're going to see. Right. So now in this case, you can calculate the magnification by using this formula, negative again because of it is inverted, and you have objective focal length, that is the F of objective, and then Fi is the eye lens focal length. So that this ratio will be closer to the magnification of the telescope. Okay, so now you can read the slides yourself a little bit. So now we're going to move into the aberration. So now this is something that happened because of the lenses, like manufacturing of lenses or thickness of the lens, or maybe some distortion of the lens. So because of that, even because of the colors that we're going to see in our visible eye, make these aberrations because of the that kind of differences that can happen, right? So basically it means it is a distortion of the image, right? How the distortion happen, that can happen because of the visible spectrum, because different colors has different wavelength that may create a image that will make kind of distorted image. Or maybe your lens thickness is maybe not exactly what we need. The thickness may be higher. Because of that, it will create a blurry kind of image that we don't want to see. And also sometimes there may be some damage that happen to the lens that will create the distortion of the image, right? So, but in this part, what we're going to discuss about the chromatic aberration. That means basically which is related to the color spectrum that we can see, right? So now we discuss about the colors, why we have the visible spectrum from violet to red. You know that we have different wavelength for those colors. Because of that, they're going to bend especially in the refraction, they're going to bend in different angle. The red light has the higher wavelength or lower frequency. Because of that going to stay with the direct light very close to that. But blue light will be, or violet light will be more bending towards or outwards, depending on the media that going to hit. right? So we discussed that in very early in the optics part. So now, what is actually happening when it hit the lens? So I have converging lens in here. So white light is here, source is here, white light go to the lens. And because of the visible spectrum, you're going to see violet somewhere here, and you're going to see the red somewhere here. Okay, so it seems that the lens is more powerful for the violet than the red, right? So that will produce the image with different location and different magnification. Because of that, you're going to see kind of distorted image in this case, right? And sometimes multiple lenses system can partially correct the chromatic aberration. So, but in that case, you need to basically, what you have to do, these two, you need to bring it to the same point, right? So by using combination or by using multiple lens system, you can reduce this phenomena to a little bit, such as like cameras and those things. We can modify accordingly to reduce the aberration. Okay, I think that's it for this section.